nationality. So it's my pleasure and honor to be co-chairing this session with Bruno Silva Santos. This is a session devoted to cancer, and inside this major target, which is Health Research Agenda towards 2030. I think we all need to know that we have important tasks to fulfill. Cancer is one of them. I was just listening Carmo about the timeline of discovery of the vaccines for COVID-19, and as she showed, everything was possible in about 1 year. Well, it's not possible to cure cancer in 1 year. It's a more complicated disease, it's not just a virus. But one thing is also for sure, the pressure to discover things, it's important, but not so highlighted as it is with a pandemic, because mostly people believe that cancer will never affect himself. It's not contagious. It's not contagious, but is there. It's the major cause of death in Western world. So most probably, since we are not very rare persons, we will die of cardiovascular disease or cancer, one of them. So you have to deal that as serious as, I will say, a slow-growing pandemic, okay? And this is our job, that's why we are here. So I'll give the word now to Bruno Silva Santos, who's going to present the first speaker.
Thank you, Luis. Thank you very much. It is a pleasure, of course, to be here. We have dedicated this session, although it's on cancer, with a focus on immunotherapy, so the immune system, for obvious biases, but also because, as you know, the last decade has been groundbreaking in the application of the immune system and immunotherapy to cancer, finally with some very interesting clinical results. And today we'll hear about research being done in our university and also with a guest from the University of Porto, Professora Salomé Pinho, the second speaker, that deal with different aspects of immunotherapy on how to apply this for cancer treatment, from using nanoparticles to looking at patterns of glycosylation as a way to target cancer, or cellular therapies for cancer. So we'll start with Professor Helena Florindo from the Faculdade de Farmácia of our university, that will tell us about research and really how we can increase efficacy in preclinical studies, of course, at this stage, using nanoparticles, and we look forward to your talk, Helena.
Good morning to all. I would like first to thank the opportunity to be here to present our work and to share with all of you what we have been doing in using nanotechnology to modulate the immune system against tumor. And of course, I thank you the invitation to be here today. So our work has been mostly looking into the ways to increase the internalization and uptake of antigens by dendritic cells. And these dendritic cells, as soon as they recognize these antigens as non-self, they internalize them and they traffic to the lymph nodes while becoming activated. And there in the lymph nodes, they will meet T cells and other immune cells to present this antigen. And hopefully these T cells will become activated, will go back to the blood circulation, and it will look for tumor cells that will express the antigens that these dendritic cells recognized. Oh, sorry. So in our group, we have been working with polymeric nanoparticles that you can see here. This is the size range of them, and also with polymer therapeutics that usually it's a polymer chain conjugated with an antigen or a drug, depending on your purpose, which size are much smaller than the polymeric nanoparticles. And today I will share with you some of the work that we have been doing with these polymeric nanoparticles regarding the activation and the modulation of the function of dendritic cells. And why nanoparticles are important, and this is work that I don't have time to go through today, but we have proven in the past that you need to have in the same system the antigen and the adjuvants together inside the nanoparticle in order to activate these dendritic cells in a way that they will have the three signaling factors that are required to have the expansion of the CD4 and CD8 T cells as effector cells. So the particles, they will enter in the cell by the endolysosomal pathway, because these particles are mostly made of polylactic acid, coglycolic. So they will be degraded in the lysosomes. They will release the antigen. The antigen is processed and then conjugated with the MHC2 molecule, translocated to the surface and presented to CD4. But while we are designing these nanoparticles, we have to be sure that their composition will allow them to escape the degradation in the endolysosomal pathway, be released into the cytoplasm in order to release the shorter peptides or a protein, depending on what you are delivering. Then this protein or the peptide, the protein after processing and the peptide after being released, it will be conjugated to the MHC1 molecule, and this complex will be translocated to the surface and presented to CD8. So in order to have this, we have shown that if you have the antigens injected as a solution or inside the particle, the activation of these T cells is completely different in terms of memory, so you will not get memory. So that's why I will share with you from that aspect the development of this system, which is fully biodegradable, in which you have inside the combination of short and long peptides. Depending on your target, these peptides were selected depending on the disease that we were hopefully trying to modulate the immune response. And together we had as well ligands of the tool-like receptors such as CpG and poly-IC. As I said before, we have shown that this is required. And also we try to understand if you are able to silence the secretion of immune suppressive cytokines by these dendritic cells by delivering an sRNA inside this platform, if this would help to overcome the immune evasion that you have inside the tumor. So I will share with you data that we got on melanoma, colorectal cancer, and breast cancer. For example, as Bruno was saying, it was dramatically changed the treatment of these patients by immunotherapy. But even though, for example, the anti-PD-1 was approved in 2020 by the European Medicines Agency for the treatment of just a small subset of these colorectal cancer patients, and even those, the percentage of response is around 30%. And if we look into breast cancer, we are talking about 20. So there is still need to improve the response of these patients to the immunotherapy, that when it works, we know that it's very effective. So we knew that this particle was able to improve the infiltration of T cells inside the tumor mass from the previous studies, but we also knew that at some point the tumor was escaping. So we took that tumor and we saw that inside of those T cells that were inside the tumor, they were exhausted. They were exhausted, they were expressing the PD-1. So we thought, okay, so let's combine the vaccine that we know that at least enables the infiltration of T cells in the tumor mass with an anti-PD-1. So you know that the vaccine expands the proliferation of T cells, so you block at the same time the immune suppression given by the anti-PD-1. At the same time, we wanted to give an agonist of the OX40 in order to overcome the expansion of CD4 T cells into regulatory T cells. So this would give us a nice synergistic approach that hopefully would allow us to control the tumor growth. So João from my group, was a PhD in my group, developed this system, and the same particle with mannose on the surface and without. Why the mannose? Because we wanted to increase the internalization of these nanoparticles by dendritic cells, promoting the interaction of the mannose with the mannose receptor. So the first, as you can see, in terms of physical-chemical properties of the product, which is important to have something that is reproducible in terms of quality. So the properties are similar depending, they are not affected by the short or longer peptides or by the presence of mannose. We have proven that this mannose is available on the surface for interaction because we use concanavalin A, which binds to mannose molecules. So if this would be the case, you would not measure the mean average size of one particle, but rather the size of aggregates. And this is what you see here. And in the electronic microscope images, you can just appreciate that the size is very similar, so the polydispersity index is very low. So we injected these particles in the animals, and what you can see here, the particles were had Cy5, labeling the polymer. And you can see that they were mainly accumulating in the lymph nodes and at higher extent when the mannose was on the surface. Then we tried to take, just to understand, because one of the reasons why nanotechnology is not something new, it's there for many decades, but if you look into the products that are in the market, the number is relatively small. And this is mostly due because we don't control the effect of these nanoparticles on the biological effect of the immune cells. So this means that then at the late stage of the clinical trials, you end up getting adverse effects that you are not expecting. So it's important to understand, because it doesn't matter, or it's not irrelevant if you have a particle composed by polymers or by lipids or by both, because this will change the way that our body reacts to this product. So we need to control that. So we wanted to characterize the immune response induced by this particle before having the immune suppression of the tumor. So we injected in naive animals the vaccine only after we inoculated the melanoma cells, and then we combined with the immune checkpoint therapies. And what you can see here, it was when the mannose was on the surface of the particles, the control of tumor growth was much higher if you compare with the one that the nanoparticles were without mannose. This combined with the immune checkpoints. This correlated with the prolonged survival, and what was also nice to see, it was the low variability in terms of the tumor volume that these animals presented compared to the immune checkpoints, which was correlating with what was being reported in the clinic. So next, we went to the real therapeutic setting. So first, you inoculate the melanoma cells, you develop the tumor, only after you start the treatment. And here it was a la depression, because you don't see any difference between having the immune checkpoint or their combination with the vaccine. We were quite surprised, because this didn't make sense with the mechanistic studies that we did before. So we took the tumors from these animals and we characterized the immune cell infiltrates that were there. And at 2 time points, at day 18, where the response was still nice, and then after exhaustion. And what you can see is that in the early time point, both of the groups had high percentage of CD8 T cells, but these cells kind of disappeared at the later stage. And no change on the CD4 was observed. So this was not due to the regulatory T cells, but we saw this high infiltration of these myeloid suppressor cells at later stage. So we thought, and this was being reported as well in clinical trials in patients that have been treated with these activate immunotherapies. So we moved next, and we combined with an inhibitor of these myeloid suppressor cells. And what you can see here, it was that this really controlled the evolution of this tumor. This model is quite aggressive. If you compare with the combination also of this ibrutinib with the immune checkpoints, 9 out of 13 animals after 65 days were alive with a group treated with a vaccine with immune checkpoints and ibrutinib, compared to the immune checkpoints and ibrutinib that only 3 animals were alive. And again, the variability in terms of tumor volume was low, which was good. So we confirmed that this effect was due to the antigen-specific immune response that was induced. And we are now exploring this platform for other cancers, such as gastric cancers, and colorectal cancer, pancreatic cancer, and brain metastases. I'll show you one example in colorectal cancer. We know that there are multiple pathways related to cancer, to immune cells, to stromal cells that promote the progression of this tumor. One of the key elements in colorectal cancer that has been reported are the M2 phenotype of macrophages. So this was one of our selected targets. And the other one, if we remember that we are targeting dendritic cells, was TGF-beta1, because it has been widely reported as being able to block the presentation of antigens by dendritic cells, to promote the proliferation of the M2 macrophages, and at the same time to block the proliferation of CD8. So this looked to us as a good candidate to silence in the dendritic cells by using an siRNA together with the peptides and the agonists. Another aspect that we explored here, it was the replacement of PEG on the surface of these particles with polyoxazoline. Why? Because PEG is widely used, but it has been reported the secretion of antibodies anti-PEG in patients treated in clinical trials or in the clinic with ADCs, for example. So we wanted to see if this polyoxazoline would avoid that secretion of antibodies. What they do is to destroy your product, so you will not have your product in circulation the time that you think. And this polyoxazoline is fully biodegradable, which is an advantage as well. So this particle had, as I said, inside the CpG poly-IC, the siRNA targeting the TGF-beta, together with the neoantigens that we selected from a cell line of colorectal cancer, MC38, that in fact was the one used in the preclinical development of the PD-1 immune checkpoints. And we combined with an inhibitor of the CSF1R receptor to block the presence of this M2 phenotype of macrophages. So first, we injected the particles in the animals, and we took the lymph nodes one day after. And what you can see is that it seems that the particles that had polyoxazoline on the surface were internalized at higher extent in vivo by the dendritic cells in the lymph nodes. And if you look into the activation markers, these were upregulated also more in these animals that were vaccinated with the polyoxazoline-based particle. So we moved further. We inoculated the MC38 cells in the animals. We treat them with the two types of vaccines. And again, what you can see here is that this control on tumor growth correlates with the data that I showed you before regarding the upregulation of the activation of dendritic cells. And again, the variability regarding in terms of tumor volume was very low. So this was the nanoparticle that we selected for the next studies, where we wanted to understand if there is any synergistic effect between the nanovaccine and pexidartinib, and also if you really need to have the intratumoral administration of a nanoparticle targeting the tumor vasculature, delivering the agonists. It has been recently reported, even in patients, when you inject CpG in the lesions, for example in melanoma, you improve the infiltration of T cells. So we wanted really to see if this is needed or not, because we had data showing that the vaccine injected in periphery was able to modulate the immune response in situ. So what you can see here, it was that the group with the nanovaccine combined with pexidartinib showed high infiltration, much higher than the controls, than the vaccine alone, for example. But also the group with the triple combination seemed to be more effective. In terms of tumor volume, no difference we could observe between these two groups. But interestingly, what we saw, it was a huge upregulation of the PD-1 in the group where you had only the combination of the vaccine with pexidartinib. So if we can avoid the intratumoral administration of a particle, it would be much better in terms of simplicity of the treatment. So what we did, it was to combine an anti-PD-1 with a vaccine and the pexidartinib, skipping the intratumoral administration of the particle. And if you compare the administration of these components in solution compared to the vaccine, to delivery of the antigens and the adjuvants inside the particle, combined with the pexidartinib and the anti-PD-1, you see that the control of the tumor growth was much better, correlating with the survival of these animals, compared to the one just with a free component. So this was another proof that the vaccine is the delivery system that is modulating and allowing you to control and improve the infiltration of immune cells in this tumor. The other example that I would like to share with you is in the triple-negative breast cancer. Again, this is a nanoparticle. Inside you have siRNA targeting the TGF-beta, and you have, as an antigen, we selected alpha-lactalbumin. That is an antigen only present in case of breast cancer or during lactation. So this can be a kind of selective, quite nice antigen, and actually it was just published this year, a clinical trial where the preliminary results are very enthusiastic. So what we did, very simply, it was to combine the vaccine with the OX40. Again, this comes from in vitro preliminary data that we did mechanistic to understand which were the major players in these tumors. I'm just showing you the preclinical data. And you can see that in this tumor that is so difficult to get infiltration of T cells, we got prolonged survival. It was interesting to see that the tumor does not disappear. It remains kind of dormant. And we just have to prove that the TGF-beta was, the production of the TGF-beta in the tumor was decreased in terms of mRNA, also at the protein level. And what was really nice to see, it was the huge infiltration of CD8 and active CD8 T cells that we found in the tumors of these animals treated with a combination of the vaccine and OX40, the high secretion of these cytokines, and also we saw a high infiltration of CD4, but not a huge difference in terms of regulatory T cells, so these CD4 T cells may be effector. We just validated this data in another model, E0771, using KRAS as an antigen that has been correlated with a poor prognosis in these patients, also in others, such as colorectal cancer, for example, pancreatic cancer. And it was nice to see that the combination of the vaccine, here we had the intratumoral administration of the vaccine to see if we could eradicate that tumor that was dormant, and indeed the tumor almost disappeared. It was very small, and the animals remained alive over 150 days compared with the OX40 alone. So this was a really good indication that I hope I convinced you that we have a platform, that it's not a unique system that will serve for everything. We need to understand the tumor and then to identify which are the targets, but then the platform allows you to deliver peptides, proteins, and oligonucleotides inside. And we have shown that we have activation of cell response, also humoral immunity, together with Luis Graça from the IMEM Institute. And this platform is suitable for different administration routes. What I showed you, it was all administered sub-Q, but we are exploring its use through the nasal route in melanoma brain metastases that Barbara, that is here, will present you later today in the poster pitch. And of course, I would like to thank all my group for all these years, the huge collaborators that we have that are very important to achieve this data, and the funding, and all of you for your attention.
So, thank you very much, Elena. Great talk. Questions from the audience?
Yeah.
Do you want to shout? Or, yeah, maybe.
Peter Joel from Medicina. The tumor microenvironment really has gained a lot of attention recently, and it's clear that it's a major driver of tumor development. How specific do you think can you use these nanoparticles or vaccines to target specific cell types, like cancer-associated fibroblasts or macrophages or neutrophils?
Yeah, these systems are quite versatile because the polymers that you use, they can be easily functionalized. For example, depending on the target, if it is on the surface of cells, for example, everyone has been trying to target tumor cells with nanoparticles coated with antibodies, for example. And the thing that has been shown is that the percentage of particles that really reach the tumor cell is very, very low. So what people are trying to do is not to target specific cancer cells, but target the stroma or other cells, as you said, the cancer-associated fibroblasts, using peptides. So this is much easier because you have a small entity on the surface that you can control really nicely the density of this ligand on the surface of the particle, because this is crucial in order to then you get a reproducible response each time that you use the particle, which has been one of the challenges developing these systems. So yes, we are exploring, for example, regarding the cancer-associated fibroblasts, a peptide versus an antibody. And from our experience, the peptides are much easier to get a product that is reproducible and targets the site at higher extension than the antibody itself.
I have a question. Very nice presentation.
Thank you.
I have a question. It's related with this question. At a certain point, you spoke about MNOs and MNOs receptors. Where was the MNOs in that case?
On the surface. Grafted, it was conjugated to the polymer. This is an important, in the past, many people were using like in-specific binding of these entities, peptides, MNOs, on the surface of the particles, but you need to get it conjugated, of course. And and that's why we showed that it was available on the surface, because it could be just inaccessible. Yeah. Exactly. So, and we have shown as well, I didn't have time to go over it today, but the data that we got in melanoma without the MNOs on the surface, was not possible. So the mannose was really driving the response, the cytotoxicity, and now what we are doing is instead of having one molecule of mannose, we are having a triple molecules, 3 mannose on the surface.
On the three? On the entire particle?
No. Instead of having just one mannose conjugated to the polymer, to have 3, because then you get high affinity. Yeah, but it has.
I'm sorry.
Sure. Go.
Yeah. You also show the image of the lymph nodes, as far as I understood. Is that the lymph nodes, or?
Which one, in the cartoon? No.
Yeah, in the cartoon. No, you have a picture. You have an image of the animals. I don't
In the animals, yeah, it's with the blue. It's a lymph node, yeah. Yes, Cy5.
How did you do that? Did you inject
IVs. We injected, we had the polymer, sub-Q.
Okay.
The same way that we injected in the animals. We have data IV and nasal to understand where they go and to see if we can modulate the immune response from the periphery in the brain. And because we don't want the particles to go to the brain, we want them to do the job here in the lymph nodes and then go to the brain. No. But we need to show to the regulatory agencies, just for safety purposes. Yeah, and we also need to show that they don't go to the spleen, to the liver, heart, kidneys.
More questions?
You go first and I'll do my first one.
I was just wondering, as you mentioned, maybe we don't need the mic as well. In colorectal cancer with current anti-PD-1, the large problem is tumors with low mutational burden, the majority of which it's not even approved as a therapy. Do you know if there is any difference, so you use MC38 as a model? Would it make a difference if the tumor has higher or lower mutational burden for your response?
We have been asked to do that proof, exactly to show if there is any, because the MC38 is a nice model to show the efficacy. So we have been tested in CT26 using the KRAS as an adjuvant. The effect is not so strong as the MC38, so it required us to go back and not only inhibit the macrophages, but we are also exploiting the CAFs on that purpose.
So it's more difficult.
It's more difficult, but you get the infiltration of the T cells and avoid the M2.
Lena, I have 2 questions in one, but first I have to take out one doubt. You talked that you used ibrutinib for give away from myeloderivative suppressor cells, correct?
Correct.
Okay.
Even though it's not specific.
Yeah, I know. That's my question. So ibrutinib also blocks phospholipase. And one of the things that happens is that phospholipase is an important mediator between EGF receptors and RAS pathway. Also, when we're talking about TGF-beta, there are now trials ongoing with SMAD inhibitors. You may
galunizertinib, yeah.
So I remember when you showed me this was our despair when we didn't see a change in the tumor volume. Then we went to see you and see a lot of myeloderivative suppressor cells. This was our answer. My question is, shouldn't we do at the same time the immune profile and if you want the metabolic or the pathways profile in the tumor to understand, because we are using drugs that sometimes may act in different manners, see, and try to understand if the overall result what is happening.
Yeah, absolutely. That's why I was saying that these particles, it seems very nice, right? You have a box that you deliver whatever you want, but it changes a lot the way and the tumor. As you were saying, we saw that, imagine if you just change one component from the formulation, even if it is a surfactant, the immune profile and the other cells that are immune suppressive, they change in the tumor. So this is exactly what we are trying to do. We have the platform developed, so now to exploit it and to make it better, we are analyzing the tumor, analyzing the pathways, and see what the platform has changed or not, or needs to change in order to optimize the composition. Absolutely, it has to be that way.
Just a very last question. Just to clarify, in terms of mechanism, you think everything is happening in the lymph node? How is the lymph node versus tumor microenvironment between these two things, right? Because some of the things you show is more activation, and priming, and some of them is a modulation of the tumor microenvironment. So how do
Yeah.
you see that?
We are trying to answer that question because we are trying now to do like mechanistic studies where we do at different time points the analysis of the immune cells on the lymph nodes, spleen, and tumor to try to correlate, and not always it's easy to correlate the effect of the particle that you have in the lymph node, but for sure it's the, and maybe this is what Luis Graça is trying to help us, is that it's the way that the particles change the interaction between the dendritic cells and the T cells. For example, Luis took the lymph nodes and sorted the CD8 and sequenced the T cell receptor, and the profile of that T cell receptor is completely different if you have the antigens inside the particle or outside. So definitely it is in the lymph node, but the consequences of that, it reflects on the tumor, but we don't have a parallel comparison yet. We need to understand.
Yes.
Thank you.
Thank you.
Now, yes, now it's my time to present to you Salome Pinho. She's our invited guest from another university. She works at I3S, and she's really the master of glycobiology. Indeed, last year she was awarded by the American Association of Glycobiology by their discoveries in the field. As probably you know, glycobiology is taking a major relevance, particularly in GI cancers, and will be something very interesting for the future to enhance the immune response. Thank you, Salome, for being with us. Thank you, and we look forward for your talk.
Thank you so much, Luis, for the kind introduction. So, first of all, good morning to everyone. I would like to congratulate the organizing committee for setting up this fantastic meeting with such a quality in terms of scientific program. A big thank also to Bruno Silva Santos for the kind invitation and also for the opportunity to present here my work. I'm going to share my screen. I hope you are seeing it. Are you seeing?
Yeah. Yes. Yeah.
Okay, so the title of my presentation is Turning Sweet on Immuno-Oncology, Glycans as Key Immune Checkpoints in Cancer. And I'm going to tell you how we can make immuno-oncology sweet from a glycobiology perspective. So I'm just going to provide a brief introduction of what we have been doing in the group in the context of immunology, cancer, and glycomedicine. So particularly we are interested on how a specific type of glycans are able to impose these tolerogenic pathways and immune suppressive networks that we know to occur in cancer, promoting the cancer progression. But on the other side, we are also interested on how a specific type of glycans are also able to impose tolerogenic pathways and autoreactive responses. And on this field, we are exploiting inflammatory bowel disease, but also other autoimmune diseases such as systemic lupus erythematosus. On top of that, we are also interested on how glycans control the dynamics and functions of T cell development as early as in the thymus development in the central tolerance, and how at the end these will define the properties of T cells by specific glycoforms of T cells, and how these associated with tolerogenic pathways, but also with immunogenic pathways. Of course, as a side project in the group, and we in the middle of a pandemic, we couldn't just stand by, waiting and see, and we decided to take advantage of our knowledge on glycoimmunology and T cell glycosylation in the context of SARS-CoV-2 infection. And we just published it in the Journal of Immunology, how T cells glycosylation can actually be associated with COVID-19 prognosis. But today I'm not going to talk about COVID. I'm going to tell you a very specific story addressing the role of glycans as important immune checkpoints associated with cancer that we just published in Cancer Immunology Research. So for those that are not familiar, I'm going to provide a brief introduction of what glycobiology is and what glycans are. So glycobiology is by definition the study of glycans, of sugar chains, Actually, for many years, the building blocks of life were considered to be the DNA, the RNA, and the proteins. And despite the major contributions of proteins and genes to address the complexity of life, we now know that the vast majority of proteins, but also lipids, are modified with glycans. And actually, the glycome, which is the repertoire of glycans expressed in a cell, in a tissue, or an organism, in fact encodes important biological information that adds to the ones introduced by the genome and the proteome. And as you can appreciate here, this is a cell surface, and as you can appreciate, essentially and virtually all our cells are covered with these dense and complex coated sugar chains that we call glycocalyx. And in fact, the glycocalyx constitutes its major biological but also physical barrier with the microenvironment. And this is because, as I mentioned, the vast majority of our proteins and lipids are modified with such a variety of different glycan structures, giving rise to a sugar code that we glycobiologists are trying to decipher. So as I mentioned, glycans are really at the interface of inflammation and cancer. And in fact, we know that during malignant transformation, changes in the cellular glycosylation occur. And these changes in cellular glycosylation is a hallmark of cancer. And the tumor-associated glycans have been described by others and us to impose pro-malignant and pro-invasive phenotypes to cancer cells. But we also know that during the inflammatory process, during inflammation, specific types of glycans also integrate in the canonical circuits that regulate both innate and adaptive immune responses, being associated with the onset of major autoimmune diseases. But the way that glycans modulate immune response has been also exploited by us in the context of cancer. So bringing again how we are dealing in my group on how glycans can be plastic and dynamic, modulating this balance and this scale between anti-inflammatory response and a pro-inflammatory response. So today, I'm going to focus on these pro-tolerogenic pathways imposed by glycans that we know to contribute to cancer progression. And in fact, as I mentioned, in cancer, the repertoire of glycans expressed by a cancer cell is completely different from the repertoire of glycans expressed by a normal cell. And along the last years, it has been described, of course, by others and us, a variety of different tumor-associated glycan structures, such as the case of an increase in overall cellulation on terminal cellulated glycans that has been associated with malignant properties and immune suppression, but also the expression of truncated glycan structures such as sialyl-TN, but also the expression of highly branched and elongated, actually abnormal N-glycan structures that actually impact every pathophysiological step of tumor development and progression from the very beginning of tumor cell dissociation by targeting, for example, an important cell adhesion molecule, which is icadiran, and in this way disrupting the cell-cell adhesion, leading to invasive phenotype, but also the example of tumor-associated glycans that target relevant receptor tyrosine kinases associated with increased signaling and cell proliferation. The example of vascular endothelial growth factor that is modified by glycans modulates the angiogenesis of the tumor, and also the example of cellulated glycans that serve as important ligands for selectin in endothelial cells, being an essential and sine qua non condition for metastases and for the extravasation of tumor cells to the formation of the new tumor foci. So in the last couple of years, we have been gathering a compelling body of evidences showing that in the cancer side, that these abnormal overexpression of these beta-1,6 GlucNAc branched N-glycans, which are highly branched, elongated, so big N-glycan structures that we have been demonstrated to impose pro-malignant properties to cancer cells, pro-invasive and pro-metastatic features. And the detection of these abnormal glycosylation in cancer biopsies has been demonstrated to be associated with poor survival rates of gastric cancer patients. But interestingly, on the side of chronic inflammation and in long-standing inflammatory bowel disease patients with an increased risk of colorectal cancer, interestingly, we also verified and demonstrated that exactly the same type of sugar chain, these branched end glycans, which is catalyzed by this specific enzyme, the N-acetylglucosaminotransferase 5 enzyme. So this branched glycan has been demonstrated to be a kind of a fine tuner of the T cell mediated immune response by modulating the threshold of T cell activation. So take into consideration these evidences showing that branched glycans impose pro-malignant properties to cancer epithelial cells, but also knowing that the branched glycans are also essential modulators of the gut immune response and integrated in this cancer equation that has been proposed by Hanahan and Weinberg in cell additions, we raised the question on whether this MGAT5, so MGAT5 is a glycogen that encodes the branched end glycans. So whether the MGAT5 mediated branched end glycans that we know to be associated with activating invasion and metastases. So what is the role in terms of immune surveillance and cancer immunoediting? And to answer this question, we used colorectal cancer as a model. Why colorectal cancer? So Elena already introduced the epidemiological relevance of colorectal cancer. So actually, in the recent 2020 Global Can report, colorectal cancer still figures on the top 3, both in terms of incidence and mortality worldwide. And actually, colorectal cancer, in colorectal cancer, we have this very nice model of progressing adenoma, carcinoma cascade. But the fact is that in colorectal cancer, predominantly in stage 3, stage 4, there is a very reduced rate of survival. So actually, the survival rates of patients diagnosed with advanced colorectal cancer, with metastatic colorectal cancer, is as low as 3 years. As it was mentioned, immunotherapy has been revolutionizing cancer therapy in the last years. But the point is that in colorectal cancer, only a minority of patients benefit from immunotherapy. And this is restricted to those diagnosed with metastatic disease and harboring microsatellite instability high and mismatch repair deficiency, being refractory to chemotherapy, which highlight the need to clarify this interplay between cancer cells and immune cells, aiming to improve the efficacy of immunotherapy in colorectal cancer. So taking this into consideration, and to answer our question, we started to analyze in the sporadic setting of colorectal cancer the expression of the protumoral branched end glycan structure. And interestingly, we observed a gradual overexpression and increased expression of the branched end glycans that interestingly reaches the highest levels in premalignancy in high-grade dysplasia, which is something that we are exploiting in the group in the context of cancer of premalignancy. So interestingly, we found that this gradual overexpression of the branched glycans accompanied the gradual overexpression of FOXP3 expressing cells, also observed at mRNA level, showing this positive correlation and significant correlation between high levels of MGAT5 and high levels of FOXP3. When we validated this correlation in TCGA database, we observed the same. So along colorectal cancer progression, high levels of MGAT5 accompany high levels of FOXP3 that suggest that these two genes appears to play together in the process of colorectal cancer development. And to gain further insights on this correlation between the branched glycans and immune suppression, we use gastrointestinal cancer cell line, MKN45, in which we stable transfected with GNT5 enzyme, giving rise to the overexpression of the branched end glycans at the surface of cancer epithelial cells. And we did some specific immune assays with co-cultures with PBMCs, dendritic cells, and T cells. When we co-culture our cancer cells with PBMCs, we observed that when cancer cells overexpress the branched glycans, we observed this significant decrease on T-beta expression in CD4 positive T cells, that was accompanied with this significant decrease on the release of these anti-tumoral and pro-inflammatory cytokine, which is interferon gamma. Interestingly, we also observed that when cancer cells overexpress the branched glycans, we observed a significant decrease on MHC class 1 expression at the cell surface, which suggests the impact of the branched glycans on immune escape. We did the same approach but using dendritic cells. So in fact, dendritic cells, as all other myeloid cells, but also T and B cells, are equipped with a variety of different glycans recognizing receptors, such as the case of DC sign of mannose receptor that Elena also talked about, but many others that still is an unexplored field of research. So we observe exactly the same trend. So when cancer cells overexpress into branched glycans are co-cultured with dendritic cells, we observe a decrease on pro-inflammatory cytokines, a tendency to an upregulation of anti-inflammatory cytokines, TGF-beta. Then, when we add T cells to the co-cultures, the same was observed, a decrease on T-beta expression, and also a decrease on interferon gamma and TNF-alpha expression in CD4 positive T cells when cancer cells overexpress the branched glycans comparing with the mock cells. So as I mentioned, immune cells are equipped with a diverse repertoire of glycans recognizing receptors, and depending on the glycan structures, these instruct a pro-inflammatory or an anti-inflammatory response. And we went to check the levels of expression of DC sign-mediated recognition of these branched glycans. And interestingly, we observed that when cancer cells overexpress the branched glycans, there is a significant decrease on DC sign recognition. So which suggests, in fact, that the overexpression of these highly complex and branched glycans appears to preclude immune recognition mediated by DC sign expressing immune cells, apparently driving this immune suppressive network through inhibition of interferon gamma. So to further dissect this mechanism, we use another cancer cell line, a murine colorectal cancer cell line, in which we CRISPR-Cas9 for MGAT5. So basically, we deleted these pro-tumoral branched glycans and inoculated in immune-competent mice. What we observed was this dramatic decrease on tumor growth. Actually, most of the mice inoculated with the knockout cells didn't develop any tumor. This is an example of this tiny little tumor mass observed when we inoculated the MC38G5 knockout cells. This, of course, imposes a technical limitation, so in precluding us to characterize the immune profile. But to overcome this, we did in vitro co-cultures in which we used our wild-type cells and T5 knockout cells, co-culture with bone marrow-derived dendritic cells from these mice, and we observed that, in fact, the deletion of the branched glycans are associated with an increased production of pro-inflammatory cytokines such as IL-23 by bone marrow-derived dendritic cells. We did exactly the same approach, but in this way, using immune-deficient mice, using the RAG2, IL-2 gamma chain knockout mice. And interestingly, we observed that when we inoculated MC38 deleted with the branched glycans, we can see tumor growth. And in fact, these highly suggest that there is a dependency on tumor-expressing glycans interplayed with immune response in order to the immunoediting can occur. So then we validated and we tested our hypotheses in different colorectal cancer mouse models. We did that in MSH2 William-Cree knockout cells. Actually, this mimics the Lynch syndrome with MSI high phenotype, but also we used the APC min plus, which mimics the familial dermatosis polyposis syndrome. And we crossed these mice, these colorectal cancer mice, with our MGAT5 knockout mice. And we observed this significant decrease on tumor growth, on the number of tumor lesions, and interestingly, an increased survival of the mice. So this suppression and this cancer prevention was associated with a significant decrease on regulatory T cells, CD25 positive, FOXP3 positive T cells, and also a decrease on the immune checkpoint inhibitor PD-1. This was also associated with an increased production of interferon gamma and IL-17A in the tumor microenvironment. So in fact, all of these evidences allowed us to propose this model, showing that when we have the cancer cells overexpressing these highly complex branched-end glycans, this creates a kind of a glycan mask that precludes immune recognition, that inhibits immune surveillance, contributing to immune suppressive networks. When we deglycosylate our cancer cells, when we remove this glycan mask, we can express other interesting glycan epitopes that promotes immune surveillance and potentiates a pro-inflammatory and anti-tumoral immune response. So, but of course, when we publish these evidences, a handful of many other questions arise that are pretty much related with this dynamic and plastic role of glycans in either promoting an anti-inflammatory response and a pro-inflammatory response, and how we can use glycans to unleash an effective anti-tumor immune response. And in fact, in the era of cancer immunotherapy, we are actually trying to remove the brakes of T cells in order to become T cells hyperreactive and promoting its effector functions. But what are the consequences of that in unleashing such an uncontrolled immune response in the tumor microenvironment? And this is actually highlighted by the fact that cancer patients under immunotherapy may develop rheumatic autoimmune-like syndromes, such as the case of colitis, of inflammatory bowel disease, but also lupus. And actually, in a recent report, it was estimated that around 7% of patients under anti-PD-1, PD-L1 immunotherapy, so the pembrolizumab and nivolumab, may develop autoreactive syndromes. So in line with these, our question is, what are the effects of glycans in triggering the opposite, an autoreactive immune response? This is something that we are also exploring in the group in the context of autoimmunity. So I hope I have convinced you that glycans are definitely an important piece of information that we need to account in the context of immuno-oncology, in the context of immunotherapy, taking advantage of the pro-inflammatory or anti-inflammatory properties. I think we are pretty much close to the clinical medicine. And these are some of the examples on how glycan science are really close to the clinical medicine. The use of glycomimetics as blockage strategies, the use of glycopeptides as vaccines design, and actually Elena also mentioned that, which is also very curious, that glycans are also included in this vaccine design, but also the concept of glycoengineered antibodies, and this has been catching the attention of the big pharmas. And in the context, for example, of IVIG, so the use of these intravenous administration of a pool of immunoglobulins in refractory autoimmune disease patients, in which it has been demonstrated that the removal of the sialic acid from the Fc domain of immunoglobulins actually potentiating 100-fold the efficacy of these IVIG treatment. But also we have glycans as a potential source of glycometabolic therapy, but also as the way that the cancer cell, for example, is composed in terms of glycans. The cancer glycome can actually have many biomarker applications in diagnosis and prognosis. And these are some of our contributions on how glycan science can actually reach the clinical medicine. And I'm finishing by thanking my group, Immunology, Cancer, and Glycomedicine at I3S. This is the fantastic Douro Vineyards in Regla, in this year annual retreat of the group. Of course, all of the collaborators, a special thank to our clinical collaborators. Without them, we couldn't do this translational research approach from Hospital Santo António, São João, IPO Porto, and Coimbra, to the international collaborators, to the agencies funding, and I will be happy to take any question. Thank you again. Yes, thank you, Bruno, for the question. So actually, we are exploring the glycans from two perspectives. From the perspective of the epithelial cells, of the epithelial cancer cells, and this study that I just presented was on the side of epithelial cancer cells. So the way that cancer cells are covered with these branched glycans, this precludes immune recognition. So immune cells cannot see the cancer cells properly. But we are also exploiting from the side of the immune response, from the side of T cells. So we have evidences in the context of inflammatory bowel disease that in fact the way that T cells are glycosylated themselves in targeting, for example, the TCR glycosylation, the CTLA4 glycosylation, this defines the effector functions, the activity and the functions of the T cells. So what we are now exploring is how T cells are glycosylated in the tumor microenvironment. And our preliminary evidences show that they are, in fact, highly glycosylated, and this precludes decrease the threshold for T cell activation, leading to immune suppression. So there is two poles of the equation, epithelial cells and T cells, and how these can synergize towards cancer immunoediting and immune response.
And could there be any impact on the myeloid compartment, on macrophages, neutrophils, by interfering with the glycosylation pattern?
Yes, that's for sure. That is on the side of epithelial cancer cells. As I mentioned, myeloid cells have such a variety of different glycans recognizing receptors that we are exploiting. They can sense and detect alterations on the cellular glycosylation, and this defines either pro-inflammatory or anti-inflammatory responses.
Mm-hmm. Thank you.
Okay, so Salome, two questions for you, and one maybe for the general people that we'd like to understand. Is we know that diabetes and obesity are linked with cancer development. Do you have any proof that glycosylation is an important process here in cancer development or not?
I agree. Yes. So this is, this connection from the glycobiology point of view is not clear. What we know, for example, is with aging, and cancer is also associated with aging. There was a quite recent study addressing this relation between highly branched glycans and immunosenescence that might be associated with cancer. From the part of diabetes, this would be a metabolic dysregulation that should be, it's not explored on how this metabolic dysregulation as well as obesity might impact on the glycosylation pathway and how this is related with cancer. This is an interesting, definitely an interesting topic to explore.
In the same line, do you know if the sugar intake in the diet, which is something very much talked between doctors and patients, can interfere with the glycosylation patterns of cancer or not? Do you know about that?
Yes, there are evidences showing that. There is a kind of a bypass of the glycolysis and of the glycosylation pathway, and there are evidences that the uptake of sugar can actually impact on promoting the exosamine biosynthetic pathway associated with promotion of glycosylation. Yes.
Okay. Now a final question for myself. Now, it's, under treatment, there is always selective pressure for the cancer cells. And unfortunately, if you are in advanced stage, they survive, particularly in colon cancer. And that's why the prognosis is so bad in stage 4. Mm-hmm. Do you have any evidence that under treatment, you may increase particularly the levels of branch and glycans in the tumor? on the T cells during treatment? I mean, this could be one of another mechanisms of resistance. Describe it. Do you have that?
We don't know. That's a very pertinent question that we really would like to tackle, how this modulation of the cellular glycome, of the glycosylation of the tumor might be associated with treatment resistant in the context of cancer, but also, for example, how this might contribute to the metastasis process, more related with this kind of seed and soil theory associated with the metastasis process. But this is a very relevant question, for sure.
We are collecting CTCs in colorectal cancer metastatic also, and we were thinking whether if you could one day study together if there is a different pattern on N-glycans during treatment. That could be very interesting. So we will
I would love to do that.
Again. Yes, we'll talk again.
Okay, thank you so much. I would love to do that.
Thank you very much, Salome. It has
Thank
been
you.
a privilege to welcome you to this session. Thank you for joining
Thank you
us.
so much.
Thank you
Bruno.
again.
Thank you. Bye-bye.
Now it's my pleasure to introduce you the last speaker. Bruno Silva Santos is one of the directors of IMM, is a major person in immunology in cancer, at least in Portugal, not only in Portugal. I told him, I think, I don't know, 2 weeks ago, 3 weeks ago, I was about 5 or 8 years ago in India for a talk in a meeting, and there was a lot of research in India asking me if I knew Bruno Silva Santos, because he's the man of gamma delta T cells.
Yeah, they are popular in India.
And because he's so much interested in gamma delta T cells, he's going to talk about a really possible pathway to treat patients with immunotherapy, with adaptive immunotherapy with dot cells. Bruno,
Thank you. Thank you, Luis. So if I can get my slides. Of course, it's a pleasure to be here in these two functions. If my slides show up, I will tell you a story, essentially, how we went from our knowledge on gamma delta T cells. I'll tell you a bit about this odd, unconventional type of T cells, and using them as a new immunotherapy for cancer. So basically, as I was asking Elena when she presented with colorectal cancer as a good example of this, we know that immune responses using conventional T cells, like CD8 T cells, cytotoxic T cells, can really vary depending on the amount of antigens the tumor presents to them. And so conventional T cells, let me see, where is the pointer? Is there a pointer? Este? Yeah, it's just slow to react. So conventional T cells that have an alpha-beta T cell receptor, like CD8 cells do. In the case of CD8s, their T cell receptor interacts with MHC class 1, and this presents peptides to them. And in the context of cancer, what's critical is that these peptides derive from oncoproteins. So they are somatic mutations that are contained as a message in the form of neoantigens, of neopeptides that can be detected by these T cells that will then react to these pseudo-foreign antigens. And so this is really critical, and it has been associated with immune responses. We know that the more antigens you present to them, neoantigens, the more likely it is that you engage a very productive immune response. And so it is of no surprise that the immune responses and the clinical responses that have come out of using the blockbusters of immunotherapy nowadays, immune checkpoint blockers, anti-PD-1, anti-CTLA-4, and so forth, these really come with tumors that have higher mutational burdens. So it's not a direct association. There are exceptions to these. There is more to the tumor microenvironment, as we know. We talked about immune suppression, etc. But definitely tumor mutational burden is an important variable, and it's a logical one. And so this creates a problem, of course, which is at this extreme of this plot, where you really have tumors with very low mutational burden. And please note this is a logarithmic scale, so there is a huge difference between a melanoma or lung carcinoma and really going all the way down, especially with hematological cancers that are very driven by very strong oncogenes, you really don't need so many other mutations, somatic mutations, besides a couple of these strong oncogenes and translocations that often occur in these lineages. So at this extreme, that includes both solid tumors but a lot of hematological cancers, we really have a problem for immune checkpoint blockers because they are just releasing the brake essentially, and if you don't have enough activation that can be engaged, you will not get a clinical response. And so many people have kind of defended this idea, and as you can see, this is already a few years old, that at this extreme of the plot, possibly T-cell therapy, using adoptive T-cell therapy, where you really select and you manipulate ex vivo what you're going to inject to ensure that these cells are able to target these low mutational endogenous tumors, is probably the best way out. And so we are pursuing this idea or this concept, and we chose gamma delta T cells to do so because one of the problems if you're going for adoptive cell therapy is this prospect of being stuck with an autologous therapy, which obviously is a major limitation. Currently, in hematology, the therapy that has been approved, CAR T cells, are autologous cells, meaning that you need the blood cells from the patient. This is obviously a huge limitation, not only time-wise, the time it takes from the moment of diagnostic to the actual production of the autologous cells, but also in terms of practicalities and having, relevant and active cells from the patient, usually heavily pre-treated, so the immune system might not be at the best shape to actually be manipulated ex vivo and then re-injected back. So we favored these gamma delta T cells precisely because they can be used in an allogeneic setting, that is, from healthy donors to treat cancer patients. And this is because the gamma delta T cells that have a different T cell receptor, not alpha beta, but gamma delta, as the name says, this TCR does not interact with MHC molecules. So it will not recognize foreign MHC, different MHC from between all of us, and so the cells themselves will not create any graft versus host disease. They will not impose this major limitation to use cells across different people. And so we can aspire to have banks of cells from which we will treat in the allogeneic setting cancer patients. And so this has already been explored in the context of leukemia, where, as you know, to treat leukemia, one can do allogeneic stem cell transplantation. And in fact, this is all data, clinical data, showing that the patients that fare the best, that really are long-term survivors, are the ones that have a high reconstitution of these gamma delta T cells. So it's those patients that upon stem cell transplantation have a very good compartment of gamma delta T cells that fared the best. And gamma delta, I should say, was the only immune indicator that allowed the segregation between the two types of groups, the long-term survivors and those that would not fare so well. And so there is also data in solid tumors. I will pass this to tell you that we decided to focus on a gamma delta T cell subtype that, as you can see here, within tumors, there are two major types of gamma delta T cells. They can either express a V delta 1 or V delta 2 chain, but within tumors as TILs, this is in the colon, the majority are invariably of the delta 1 type. This is only relevant because our therapy will be called delta 1 T cells, dot cells, so that you understand where dot comes from. It's because the cells express a V delta 1 chain, and this characterizes the subtype of gamma delta cells that really infiltrates tissues, including tumors, much better than the other subtype, the delta 2. As you can see, in our peripheral blood, we actually have much less of the V delta 1s than the V delta 2s. And this is precisely because the V delta 1s like to live within tissues. They infiltrate tissues and they are rare in circulation. Of course, at the same time, the prospect was good to get a T cell that would like to home to a tumor. The problem is to generate an adoptive cell therapy. Obviously, the easiest thing is to access blood from people, especially healthy donors that we want to be the providers. And so the real challenge to begin this project was that the population we want to expand and have a cell therapy based on is very rare in the blood. So in the total white blood cells, this is a leukocyte gate in the blood, you have 0.3% in average of the cell type we want to produce billions of. So this project really initiated with a PhD student in my lab, my first ever PhD student, then became a postdoc, then a member of the company. So he has done a long trajectory within the lab and the company we started, called LymphAct, a spin-off of IMM. So Daniel was the visionary in the sense, because once he got this kind of data, which was a protocol, I'll tell you a little bit about the protocol in the next slide, but this is the outcome. As you can see, each line is a different donor, and as you can see, we found out a very robust way of expanding thousands of fold these very rare cells. From each V delta 1 cell we take out of the blood, we'll produce around 10,000 cells upon 2 to 3 weeks. Now we only need 2 weeks of ex vivo expansion. And so, as you can see, these V delta 1 cells that we wanted to be the part of our product really become the dominant population, and this led us to really take this protocol that you can see here a bit more detail. So it has a way of activating T cells, it has an antibody to trigger the T cell receptor throughout the protocol, and then has a cocktail of cytokines that Daniel only got to in a very unbiased way, because you may have not noticed, but the poor guy needed to test almost 2,500 conditions to get to this final protocol. So it took him 2 years to define the protocol. But once we had the protocol, we could apply it. And so what we decided to do was to generate large numbers of cells and test it in several preclinical models. So besides expanding the cells, what was very clear to us was that we were changing the repertoire of receptors on the surface of the cells. These are 4 very important receptors that are typically found on natural killer cells, and that our T cells, upon these 2 weeks of culture, now acquired these 4 receptors. So basically, we were converting a T cell into an NK cell, and the K in NK says it all, is a natural killer. These are cells very good at killing. And we proved they are very good at killing, our dot cells, because when we tested them against all these type of cancer cell lines, in this case, they were able to target all of them, essentially, regardless of their origin, from a solid tumor to hematological cancer. They did not show any preference. They were really pan-tumor in that sense, in being very cytotoxic, and these are 3-hour assays where essentially all the tumor cells are gone. As a proof of concept, we decided to start with an hematological cancer because of the reasons I told you. This is where checkpoint inhibition was not acting so well. And for the case of AML, a case where CAR T cells have not been developed yet. So it's very difficult to target just the tumor cells with CAR T cells. And in the case of myeloid cells, you cannot live without them. So you cannot wipe out the healthy myeloid cells in your body. So CAR T cells have not made the clinic yet with AML. So we decided this is a good. There have not been any groundbreaking treatments for over 40 years. Chemotherapy is still the standard. And so we decided, let's go for AML. So cutting a long story short, I'll go fast, because basically I just want to tell you that these cells were able to kill essentially all types of AML cell lines, representing the 6 major subtypes of AML. Of course, AML primary samples from patients themselves were also targeted and very similar to the cancer cell lines, so it was not an aberration of cell lines. Primary cells were also targeted very easily by these cells, even if the cells had been selected for chemoresistance, because we always thought these patients would get to the cellular therapy after failing chemotherapy upon resistance to the standard chemo. So if you select the cancer cells for chemoresistance, which is this group here, they are essentially as susceptible to dot cells in a dose-dependent manner as chemotherapy naive cells. So basically, you can use these T cells after the chemotherapy has been given, and the T cells are very specific to the tumor cells, because if you test them against healthy cells, they do not target any healthy cell in the blood, or even in solid tissues. We tested fibroblasts as an example of healthy tissue. So let me just tell you that these NK receptors are very important for recognition. We did a lot of gene expression for the ligands for these receptors, and there was one receptor, DNAM1, that is here, has 2 ligands, ligands in yellow, and they had a very strong expression in tumor cells, and they were essentially absent in healthy cells. So we formally wanted to show that these ligands were important, so we used CRISPR-Cas9 to take out the ligands on the tumor cells, and as you can see, there are two ligands, as I told you. If you take out one, you reduce around 30%. If you take out the second one, you reduce down to 50% of the reactivity. We still have 50% left, and we think it's the other NK receptors, and we are formally now doing triple and quadruple knockout lines with other candidate ligands from all this panel that I showed you before. So there are ligands for all these 4 receptors. DNAM1 seems to be very important because it can account for around 50%, and now we have to conjugate with these other candidates there to really know how these cells are acting. Finally, just to tell you that these cells act in vivo by really reducing the tumor burden in both xenograft models. So this is human AML, either primary AML or cell lines, injecting into immunodeficient mice, and then treated with the dot cells. It can really reduce tumor burden both in the blood and in target organs, and where the tumor disseminates to. In different models, it's not AML specific. This is another hematological cancer, chronic lymphocytic leukemia, where the impact was even more striking. Look at this control group where you have a lot of human B cells that are the tumor cells in the bone marrow, and essentially they are completely gone in mice treated with dot cells, and this is validated by histology. And so with all this, we were able to convince or be attractive to a British company that acquired our small Portuguese company that lived exactly for 5 years before it became part of this bigger group that is now owned by Takeda, the pharmaceutical company, and together with them we managed to enter and start our phase 1 clinical trial only 2 months ago. So we are very happy to be at this stage. This made the news, blah blah blah, but essentially what's important is that not only is as for now safety has been tick the box with the lower doses. This is a dose escalation, so the low doses used so far have been very safe. We will escalate and determine the maximum tolerable dose to enter the phase 2. And just to say that this is relevant for our research here at the University of Lisbon, because beyond the clinical program now taking place in the US, where Takeda develops the oncology program, we are benefiting from a sponsored research agreement with a company that funds our own research, and essentially the key is to repurpose this therapy for solid tumors. So we are producing the same kind of data in preclinical models, but now for solid tumors, starting with something that has been constant in the 3 talks we had today, which is the big unmet medical need of colorectal cancer. And this is just some preliminary data showing you that dot cells can really have an impact on CTCs, on circulating tumor cells. So what we do in this assay is that we establish an orthotopic model of colorectal cancer. It's a human colorectal cancer cell line with very low mutational burden, for which checkpoint inhibitors do not work well. This is called SW620. And then we can treat these animals with dot cells after the tumor is already visible, like you can see, by Illumina, by bioluminescence. So you have a big flashy tumor when you start treating. And essentially what you do in this experiment is after 1 month, you take the blood of the animal and you culture the blood to test for growth, as you can see, of circulating tumor cells. And the untreated group is full of tumor cells that grow very well on these plates. And as you can see, the dot, in this case, is already the product from the company called GDX12. The product treated groups in 4 different animals, essentially we cannot get CTCs growing. So this is very promising for us. This, as you can see, is a 1-month experiment. To get to the metastatic stage, we need to allow 3 months. So these are very time-consuming experiments, but we have our hopes high that we'll have impact on the metastatic disease by treating, of course, at least with 4 doses of DOT. As you can see, we have to favor the activity of these cells, but we hope to be able to produce this preclinical data. And with that, I will thank you for your attention and just say this has been a great avenue that we went through with Danielle that was really key to this project, and thank the rest of my lab and all of you for your attention. Thank you. Everyone needs to go for lunch, as you can see. But we have time for
There's
questions.
a lot of questions.
I'm just
lot
wondering
of
that the
questions.
entire audience...
You want to escape. It's
They all escaped.
motivation.
Thank you very much for staying, for controlling your hunger.
Yeah, please. That doesn't matter. Doesn't matter.
Hi. Thank you.
My first question is how much it costs to produce the dot cells?
Oh my God, that's a bad question, especially for me, because I don't want to enter conflict with Takeda, right? Because they will have... So when we did the business model and so forth, right, we were estimating, and that was a big thing because CAR T cells, as we know, the treatments were costing at that stage, you know, hundreds of thousands. We were estimating at the dozens of thousands, so around 10,000. Our prediction was 10,000 to produce the treatment, but that was in our naive Portuguese scale business model. Then you multiply by the zeros of the pharma company, of course, unfortunately.
If I can have a question that will help to perspective if it is expensive or not. This is a treatment to be performed in which way? Every week or once?
Yeah, so that is a very relevant question, right? Because we don't know how long we will continue to treat. We are conceiving up to 3 infusions of cells. Okay. 2 weeks apart, because we know we are doing the allogeneic setting. We know for 2 weeks the cells are not rejected by the host himself or herself. After 2 weeks, we should reinfuse cells to allow the product to be constantly active. And we think that at least for 1 month, we need to have the cells in to target the tumor. Hopefully, we will not do more, but of course,
but
you know how cancer acts.
There is any memory that stays there against the tumor?
Because, exactly. So we think the cells, this is our hope, that there will be a pool of cells that will remain. Although the majority of the cells will go, there will be a pool of cells that will remain. But we'll have to test
so
if
that
this
depends
is possible,
on results.
even
if
in the
you
allogeneic
have with
setting.
3 or 4 administrations at total cost 40,000 euros, it's not expensive.
Yeah, we'll see.
Okay?
What will make this much cheaper is the allogeneic setting. So our prediction is from 1 donor we can treat around 20 patients. So the scalability of this will be the advantage. Okay. But we have the problem that we need to tackle, which is exactly as you say, how long will the cells remain? Will there be memory? And so we are already manipulating our dot cells to take away potentially their own MHC so that they cannot be recognized by the host immune system. So.
I have a question. Maybe you explain this, but how do you select the patients that will benefit with the dot cells?
Yeah, that we have no idea for now, which is very relevant. I mean, the reason why we are focusing on this recognition, the molecular recognition, is that if we have a sample of the tumor, we would favor patients that have the ligands expressed on the tumors that would match the recognition. A bit like PD-L1 for PD-1, but as you know, PD-L1 does not explain everything. We fear that we might fall on the same scenario, which is there are patients that benefit although they don't have the ligands, and that's because we lack enough information about other things.
Should be the DNAM1, no?
Yeah, the DNAM1. Yeah, the DNAM1 ligands would be an obvious biomarker, let's say.
No.
Very impressive.
Thank you.
It was my first contact with this type of work, actually.
Dot cells.
Not
Dot
much,
cells.
but I didn't know in detail what we was doing, and it's really impressive. So you
Thank
have cells that kill everything.
Yeah, well, let's hope not everything, just tumors. That is the...
When you start presenting about works on cancer cells, I was worried, but then you present the normal cells.
But because it's the first time we're using them in the clinic, as you can imagine, this phase 1, we went very, very carefully. So the first dose is almost homeopathic. You know, and the dose escalation is very careful because of that. We don't predict side effects. The mice didn't show them, but it's mice, it's not people, right? So let's see.
I actually have 2 questions. So first one, maybe this is a naive question. So for each cell is specific for a specific target, let's say for a cancer cell. Is that
You mean different tumor types?
general cell that kills everything?
No, we think it's quite universal. So now there is this prospect. So, and this is the attractive thing, but you need to know how real is that universality, right? So we are testing that in the mouse models and preclinical models. We can take dot cells produced from a healthy donor to treat different types of tumors of unrelated people with different origins. That does not mean it will target every real tumor in the real person, right?
Yes,
One
yes.
thing is what we do in the lab.
No.
In the lab,
Yes.
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 But the reality, we'll see it in the clinic.
Preventive immunotherapy.
Yeah,
See?
yeah,
See?
exactly,
No cells.
exactly.
Yeah.
Yeah, preventive immunotherapy.
And I have a second question related with, because at a certain point, is this 100% immunological, let's say, mechanism of action?
It's a very good question.
Is that, because at a certain point you start speaking about ligands
Yeah.
and some peptides
Yeah.
appeared, and maybe there is some kind of
Immunological, yeah. No, it's a very good question. We don't know how the dot cells manipulate the tumor microenvironment beyond the immune compartment, right? We have no idea. And the preclinical models we use are very restricted. So unlike what Elena, for instance, was showing, which are syngeneic models, mouse therapy in mice, where you have all the components, we are doing this human tumor and human dot cells into an immunodeficient mouse. So we are lacking the matching of human nature in the tumor microenvironment. The fibroblasts, you name it, everything else is mouse. And this is the problem. Our dot cells are exclusively human. We cannot produce them from mice themselves because the cell type and the molecules they express, unfortunately for us, are not conserved in mice. Many of these NK receptors are pseudogenes in mice. They evolved in primates. So we could only do these experiments as a real dot cell in monkeys, which obviously we did not want to do. But, so we lack syngeneic animal models. We have to jump into these very artificial immunodeficient mice with human cells. And so the crosstalk between the human dot cells and the other human cells, fibroblasts, you name it, and so on, we don't know. I mean, we can mimic in culture. That's what we do. They do not target the healthy fibroblasts, and we are happy. Yeah.
But one can think about that, and somehow those cells can interact with some specific.
I know they interact with a lot of cells for sure.
Yeah.
Chemical entity, let's say.
No, I mean, one thing they do, for instance, that is a bit like that, is they create their own particles, because once activated, they secrete these exosomes, these small membrane fragments, exosomes that can go. Imagine, but I'm not studying them, but they are there.
Okay.
But Luis likes them a lot, and
No.
Bruno in Lisbon studies them.
Listen, Bruno saying, "Do you believe in exosomes?" I said to Bruno, "This is science. It's not believe or not believe. They exist or do not exist."
So as you see, I am open-minded. I even talk about them even if... Yes, I'm not. But the other Bruno, he's even called Bruno, right? The other guy, so...
Yeah.
Costa.
Other Costa. Okay. More questions? Yes, more. Peter?
Thank you.
You said at the beginning that in peripheral blood you have only 0.3%
Yeah.
of these cells.
Yeah.
Are you aware of any condition that under physiological conditions this percentage might get up?
Yeah, so it increases in CMV infection. So these cells react to viruses, and so in CMV patients, they can be high. Actually, if the donor, one of the criteria to select donors, we have to check their CMV status and look at how much the V delta 1s have expanded in response to the virus. Because if they have responded a lot to the virus themselves, they will not expand very well in vitro. They are semi-exhausted already. They've done a lot of job against CMV. They will not like our protocol for 2 weeks. So in our healthy donor pool, we prefer either CMV negative donors or CMV positive, but they have not expanded V delta 1s above 1%, for instance. When it goes above 1% in circulation, is a result of chronic activation by viruses. That's what they respond to naturally, let's say.
Can
Be some kind of induced activation, explaining why some people are able to combat tumor initiation and initiated cells, and then
Yeah, there could be definitely crosstalk between. Definitely.
I'll take your question to say, what about bisphosphonates? Because this was...
That's
they do expand gamma delta 2?
No, not V delta 1. So the bisphosphonates, they accumulate a class of phosphoantigens that only their cousins, the V delta 2s, are responsive to. So our therapy will not benefit from bisphosphonates. The V delta 2 does. Yeah.
Okay. Any more questions?
Lunchtime.
I think it's great. Bruno, was fantastic.
Thank you very much.
Indeed.
Well,
it was a great pleasure and a great honor to have you.
Thank you, Elena.
Thank you, Elena.
Salome.
Thank you, Salome. Thank you to everyone.